Nanobots sound like science fiction. Tiny robots swimming through your blood, repairing organs from the inside, hunting diseases with perfect precision. But the real story is far more grounded and far more fascinating. Nanobots are not miniature robots in the human sense. They are not tiny machines with arms, motors, or microchips. In reality, nanobots are functional systems operating at the scale of atoms and molecules, where the laws of physics behave very differently from the world we see. The word nano means 1/1000th of a meter. This is the scale of proteins, DNA, and viruses. To put it into perspective, a human hair is tens of thousands of times thicker than objects in the nano world. At this scale, gravity becomes almost irrelevant. Friction works differently. What dominates instead are electrostatic forces, chemical bonds, and random molecular motion known as Brownian motion. If you like similar educational content, please like, subscribe, and share the video with your friends. When people imagine nanobots, they often picture tiny mechanical surgeons actively navigating the body. That image comes from thinking in macroscopic terms. Real nanobots, more accurately called nanomachines or nanostructures, operate on completely different principles. They do not move the way vehicles move. They do not think. They are designed to react, not to decide. In practice, a nanobot can be a single molecule or a small molecular structure engineered to behave in a specific way when it encounters specific conditions. Its function is embedded directly into its physical and chemical structure. When the environment changes, the nanobot responds automatically, without computation or awareness. A useful analogy is a lock and key. The key does not understand the lock. It does not analyze it. If the shape matches, the mechanism opens. If it does not, nothing happens. Nanobots work the same way. They are designed to bind to specific molecules, cells, or surfaces and trigger a precise action once the correct conditions are met. Another crucial point is that nanobots are not always mobile. Some do move, driven by chemical reactions or external magnetic fields. Others are completely passive. They simply remain in place until the right target comes close enough. In the nano world, motion is often controlled by the environment rather than the object itself. Here is the most important reality check. Many nanobots already exist today, just not under that name. Drug delivery nanoparticles, DNA-based nanostructures, artificial enzymes, magnetic nanoparticles. These are all real technologies currently used in laboratories and medicine. None of them are universal. Each one is designed for a single, narrowly defined task. So nanobots are not tiny robots breaking the laws of nature. They are carefully engineered systems that exploit the laws of physics and chemistry to do things that would be impossible at larger scales. And that is exactly what makes them so powerful and so controllable. Once we leave the familiar world of gears, motors, and circuits, engineering changes completely. In the nano world, nothing is assembled by hand. Nanobots are not built piece by piece. They are designed to assemble themselves. The task of the engineer is not construction, but control over how matter behaves at the level of atoms and molecules. The core principle behind most nanobots is self-assembly. Instead of physically connecting components, scientists design molecules so that they naturally arrange themselves into a desired structure. This happens because of chemical bonding rules, electrical charges, and molecular geometry. If the design is correct, the structure forms automatically, without external intervention. One of the most powerful building materials for nanobots is DNA. Not because of genetics, but because DNA is an incredibly precise construction medium. Each DNA strand binds only to its complementary partner. This allows researchers to program DNA to fold into specific three-dimensional shapes, boxes, cages, hinges, or containers using predictable rules. A practical example makes this clearer. A DNA-based nanobot can act as a microscopic drug container. In normal conditions, it stays closed. When it encounters a chemical signature typical of diseased tissue such as a specific enzyme or acidity level, it changes shape and releases its payload. No electronics, no external commands. Response is purely chemical. Nanobots can also be built from inorganic materials. Gold nanoparticles are widely used because they respond strongly to light and heat. Iron oxide nanoparticles can be controlled by external magnetic fields, allowing scientists to guide them inside fluids. Carbon nanotubes offer exceptional strength and electrical conductivity at extremely small sizes. A key concept to understand is that nanobots do not have engines. At this scale, motion works differently. Random collisions with surrounding molecules constantly push nanostructures in unpredictable directions. This is known as Brownian motion. Instead of fighting this chaos, nanobots are designed to use it. Some nanobots move by creating chemical reactions on their surface that generate tiny gradients in concentration, producing directional drift. Others simply float and rely on probability eventually encountering their target because there are so many of them. In many cases, movement is not required at all. The nanobot waits, and the environment brings the target to it. Another crucial point is control. Nanobots do not run software. They do not process information. Their instructions are encoded directly into their shape, surface charge, and chemical sensitivity. When specific conditions are met, a specific reaction happens. When they are not met, nothing happens. This makes nanobots extremely precise but also extremely limited. A nanobot designed to react to one molecule will ignore everything else. That is intentional. Broad behavior would be dangerous and unpredictable in such a complex environment. This leads to the central challenge of nanotechnology: how to guarantee that a nanobot behaves exactly as intended, and only where it is intended. At the atomic scale, even tiny changes in temperature, acidity, or molecular composition can alter outcomes. When the discussion moves from theory to real laboratories, one fact becomes clear very quickly: nanobots are already in use. Not as universal microscopic robots, but as highly specialized tools designed to perform one precise function better than any macroscopic technology could. The most advanced and impactful field is medicine. The human body operates at the cellular and molecular level, which makes nanotechnology uniquely suited to interact with it. Traditional drugs spread throughout the entire body. Nanobot-based systems allow localized action, reducing side effects and increasing effectiveness. One of the most important applications is targeted drug delivery. A nanobot can carry an active substance and release it only when it encounters very specific chemical conditions. These conditions may include a certain acidity level, the presence of a particular enzyme, or a molecular marker typical of diseased cells. The nanobot does not recognize illness conceptually, it simply reacts to chemistry. A practical example: instead of flooding the entire body with a powerful drug, nanostructures can deliver it directly to cancerous tissue and activate only there. This approach dramatically reduces damage to healthy cells and is already being tested and used in experimental therapies. Nanobots are also used in diagnostics. Some nanostructures function as ultra-sensitive sensors. They bind to specific molecules in blood or tissue and change their physical properties such as fluorescence, electrical conductivity, or magnetic behavior. These changes can be detected externally, allowing doctors to identify diseases at extremely early stages, sometimes before symptoms appear. Another important category involves magnetically controlled nanoparticles. These can be guided through fluids using external magnetic fields. They do not navigate independently, but they can be concentrated in specific locations, heated locally, or activated to trigger chemical reactions. This technique is used in certain cancer treatments and imaging technologies. Outside the human body, nanobots play a major role in materials science and industry. Nanostructures are used to create surfaces that repel water, kill bacteria, resist corrosion, or selectively filter molecules. In these cases, nanobots do not move or act independently. Their mere presence changes how a material behaves. In chemical engineering, nanostructures are widely used as catalysts. They accelerate reactions, reduce energy consumption, and enable processes that would otherwise be inefficient or impossible. In water and air purification, nanomaterials can trap heavy metals, toxins, and microorganisms with extraordinary precision. Each nanobot is designed for one narrow task. Once that task is complete, it deactivates, breaks down, or is removed by natural processes. This limitation is not a weakness, it is a safety feature. The idea of general-purpose nanobots remains firmly in the realm of science fiction. At the nanoscale, complexity increases risk. Uncontrolled behavior would be catastrophic. That is why real-world nanotechnology prioritizes simplicity, predictability, and control. This brings us to the final question. How far can nanobot technology realistically go, and what are the hard limits imposed by physics, energy, and safety? When people imagine the future of nanobots, they often picture self-aware machines repairing organs cell by cell, or swarms of autonomous robots transforming the world from the inside out. These visions are compelling, but they ignore the most important factor of all. Physics sets hard limits that no technology can cross. The first and most fundamental limitation is energy. At the nanoscale, there is no room for batteries, fuel tanks, or processors. A nanobot cannot store energy in any meaningful way. Every action it performs must be powered by the environment, chemical reactions, light, heat, or externally applied magnetic or electromagnetic fields. When that energy source disappears, the nanobot stops functioning. This alone prevents long-term autonomous operation. The second major limitation is control. In the macroscopic world, machines can be monitored, updated, and shut down. At the nanoscale, this is impossible. Individual nanobots cannot be tracked or commanded in real time. Their behavior must be fully determined in advance, encoded directly into their structure and chemistry. This is why modern nanobots are designed to be simple, single-purpose systems, rather than adaptable machines. The third constraint is environmental chaos. Inside the human body or an industrial fluid, nanobots exist in a constant storm of molecular collisions, temperature variations, and chemical fluctuations. They do not move along planned paths. They are pushed, rotated, and scattered by their surroundings. Designing reliable behavior under these conditions means designing reactions, not movements. For these reasons, the future of nanobot technology follows a clear direction: maximum specialization with minimal autonomy. Nanobots are not meant to think, learn, or evolve. They are meant to perform one precise function under specific conditions and then deactivate or break down safely. The goal is not to create living machines, but temporary tools that disappear once their job is done. The real power of nanobots lies not in intelligence, but in precision. They allow science and medicine to operate at the level of individual molecules, where diseases begin, where materials gain their properties, and where chemical reactions truly happen. The nanobot revolution will not be dramatic. You will not see it. You will not hear it. But it will quietly transform medicine, materials, energy, and environmental protection in ways that were previously impossible. Nanobots will not replace doctors, engineers, or machines. They will extend human capability into the molecular world. And that is where the most profound changes always begin.